The Arizona Signal Watcher DXing video blog. Episode 5, 6 meter Yagi Part 1, Intro and Design. So for this project, I'm putting on my hat as an amateur radio operator, K7HKR, and this is going to be an antenna for the 6 meter band, 50 to 54 megahertz, also known as the magic band, and that's because you get a lot of interesting propagation at this frequency range. Now, of course, you can use 6 meters for local communications via the typical ground wave or line of sight propagation, and in some locations there are repeaters on the 6 meter band. But I'm not really so interested in that. I'm a lot more interested in long range propagation, and that involves the ionosphere. So we get a couple of interesting things happening on the 6 meter band, and also other frequencies as well, but 6 meters tends to be the best one for this. And that is sporadic E, or E sub S, and that involves localized enhancements in the ionosphere above certain points, and that allows VHF signals to be reflected back to the ground. You also have transequatorial propagation and other types of instances of propagation that also involve the highest ionospheric layer, the F2 layer. The catch, though, is that these types of propagation are very time and location sensitive. So this is not the frequency band for doing long distance communications just at any random time. And for some people that's a negative, but for someone who's interested in propagation, this actually can be very exciting, because these openings can be very sudden, they can be very strong, and you can get some really interesting DX with those. And because it's very location sensitive, that's why a directional antenna is so important, because at any given time, especially when you're talking about sporadic E, you may only be getting DX signals from one direction. And so you don't really want to mess with the other directions. You want to have as much gain as possible in that particular direction to enhance the probability that you can make a contact. And so that's where the Yagi comes in. The Yagi, or Yagi-Uda, or call it a beam antenna. Now, an antenna like this, because it's not just a simple dipole or a simple vertical, there are a lot of design issues to consider. I put size, portability, and complexity kind of all together. If you have a huge amount of room to work with, well, you can make these a Yagi antenna for 6 meters with a very long beam, 20 feet or more. And that means that you'll probably have a lot more antenna elements on it. That will increase the complexity, will very much decrease the portability, but if you have a good permanent installation up on a tower and you can put up a large antenna, then that's great. Now, for this project, I'm looking at something that's a little more portable, and something that's relatively small, has a relatively small footprint, so you have a better chance of being able to use this if you don't have a lot of space available. Forward gain. Well, the whole point of these multi-element antennas is that the elements combine together to do something interesting with a pattern. And in this particular case, what they do with the pattern is that it focuses most of the energy in one direction, the forward direction, as we would call it, and that means that you enhance the gain in that direction. So the antenna is more sensitive receiving in that direction, and a larger fraction of the antenna power goes into that particular direction. And so you don't waste energy transmitting in directions that you aren't concerned with. The front to back ratio, well, that's kind of related to all that, because typically what you want to do is that if you're only going to be transmitting and listening in a particular direction, you don't really want to deal with any signals that may be coming in from any other direction. And so you can design antennas with a substantial front to back ratio, where in the forward direction it'll have a certain gain, and in the backward direction you may be talking about more than a factor of 100 diminished signal relative to the forward direction. Side lobes, well, that forward gain, you want it usually to be concentrated into as narrow a range of angles as possible. And so even if you have a good front to back ratio, some designs you can have a lot of energy going off to the side, which doesn't really affect the front to back ratio, but does affect what fraction of the energy is going in the direction that you want. Bandwidth and band center. Well, band center is obvious. You want this, you want it centered somewhere in the 6 meter band. But there are some subtleties there, because depending on how you design the antenna could be a very narrow frequency range, and that's where bandwidth comes in, because the design can be a little different if you say want to cover the entire 6 meter band to cover all the different modes from Morse code and single sideband and FM, and maybe you want to communicate with repeaters sometimes, versus optimizing it for, say, single sideband or for CW, where you only need to optimize for a narrow portion of the band. Impedance, 50 ohm feed line, and you can design Yagis relatively easily that have 50 ohm impedance at the feed point, and so that makes things very convenient. Now you're still going to want to have a balun there, a 1-to-1 balun, but it does mean that you don't have to worry about having a transformer where you need to transform from, say, 200 ohms to 50 ohms or something like that. And the SWR, that's kind of related in here with both the impedance and the bandwidth. You want to have a good a good SWR covering the bandwidth that you have, but you do want to make sure that that is fairly low, and it would be nice if you had that maximized or minimized, I guess, as close to 1-to-1 as possible in a frequency range that you're particularly interested in. So for instance, you could have the lowest standing wave ratio, say at the low end of the band where you're working single sideband and CW, and maybe still have a good SWR at higher frequencies, but you're not as worried about being as optimized there. For design, that's where you have to go to software. Now there's a variety of software packages for different operating systems to model antennas, and most of these are based on what's known as the numerical electrodynamics code, and various versions of that. The free programs tend to use version 2.0, which is fairly old but works okay for fairly simple antennas. There's also higher versions which usually require a license. Now I use Mac and Linux systems, so what I'm using for the modeling is something called COCO NEC, C-O-C-O-A-N-E-C, and this is version 2.0 of that program. But again, there are a variety of programs out there for different operating systems, and they're going to give pretty much the same results for relatively simple antennas, and this is still a relatively simple antenna. I don't want to go into too much detail on the particular software, but basically what you do is you construct an antenna out of individual elements. And so for the Yagi antenna that I'm constructing, I decided to make it 4 elements, and I wanted to try to fit it into a relatively short beam, and that was something that I kind of had to play with a little bit. And as I was playing with it, I decided that I wanted to try to get it down to a 7-foot beam. And so the geometry of this, now we're looking at an angle here. So here's the driven element. This is the dipole element that has the feed point. That's what that little circle means, is that there's a feed point there. And then I have one reflector element and 2 director elements. The director elements are out in front. The reflector element is in back. Those collectively are called parasitic elements because they're not they're not directly attached to your radio via the feed line, but they strongly influence the overall antenna pattern. Any metal objects near your driven element will influence the pattern. And for this, I decided to go with, to model this with half-inch diameter elements, namely half-inch diameter aluminum tubing. Now you can use hollow elements because at these frequencies the current flow is absolutely dominated by the skin effect, and a very thin skin effect. So basically the outside diameter is what's important for defining the antenna. Now, as we're going to see, the middle 6 feet of the element is going to be half-inch diameter or quarter-inch radius aluminum, and then I'm going down to a little bit smaller radius that will slide into the half-inch diameter tubing, which we'll get to later. So I've defined my 4 elements. This is in meters. And of course you can change that to English units in most software packages. And so I've got these different length and spacing of elements, and I'll show you those in detail in a moment so that you can easily read them. But what I want to do is go ahead and show you what the model looks like. Now, for my particular situation, I have a relatively poor ground. And so that's what I'm using here in the modeling. This will work in different ways in different software packages, but usually they'll give you a range of different possible grounds to work with. You can model it in free space. I'll talk about that in a moment. But I'm using a poor ground. Also, this particular Summerfield Norton approximation, that takes a little longer in CPU time, but modern CPUs do this stuff very quickly, so that's something you should pretty much always use. And you can define a set of frequencies for modeling the antenna. So here I had it set here for 50.0, 50.1, 50.2, 50.3. What I'm going to do is going to change that a little bit, just so you get a little bit of a feel for how it changes. So this is going to be 50, 50.3, 51, and 53. So I'll run that. Of course, the geometry didn't change. But let's take a look at our patterns. And this is the azimuthal pattern. And this is basically telling us, this is giving us the pattern if you're looking at the antenna from overhead. And this gives you the directionality of the antenna. So the forward direction of the, in this case, of the with the best gain is indicated here at 0 dB, and then everything else is relative to that. Now, one of the things you can see is that if we go to the red antenna, that is 50 megahertz, and you see the back end of that. There's the 30 decibel circle, so that gives us about a front to back of about 27 or 28. Green does even better. The front to back there is better than 30. Purple, it starts to get worse, and then by the time we get up to 53 megahertz, that starts to get quite a bit worse. And that's characteristic of this particular design, is that it works best at the low end of the 6 meter band. Now the elevation plot, this is very important because people will quote gains from these antennas that you're not going to see when you're working DX on 6 meters. And here's the reason why. Because of the ground. And basically, unless your antenna is pretty high above the ground, preferably a wavelength or more, the pattern is going to be shifted upward. And in fact, I have this set up so to where I can generally get this up to it's about 11.5 feet, 3.5 meters. And with that setup, the peak radiation pattern of this is at 20 degrees above the horizon. Well, that's totally useless for DX, okay, because those signals come at a very large distance, and that means they're going to be coming at very small angles. And so instead of being up here at the peak, you're going to be down many dB from that peak. And that's why it's a little dangerous to look too much at exact forward gain figures. Now you can use it as a comparison for different designs, but just remember that your forward gain that you're actually going to get for DXing is going to be quite a bit less. And that's what I've done here in the azimuth plots. These right now are set up for 5 degrees, but even 5 degrees is really a little too high. If I switch this to 3 degrees above the horizon, which is a little more realistic for working DX, you don't see any big change, but this number here changed. And this is the forward gain relative to an isotropic radiator. So that would be a perfect omnidirectional antenna. And you can see it doesn't really have any gain advantage over that, but that's just because we're looking at such a low angle. The maximum gain here is about 12 dB over isotropic. And that's a pretty decent number. But just remember that that's at an angle that you're probably not really going to be using. Now the other thing that you really want to look at here is in this particular software package is called the scalar tab. And what we're looking at here is the standing wave ratio as a function of frequency. Now this it interpolates to this curve here, and what I'm going to do is I'm going to do what's called a sweep here. And I'm going to sweep from 50 to 54 in the maximum. It'll do 17. I think it'll do either 16 or 17 steps, and that'll define this a lot better. And what you're seeing here is the standing wave ratio that's been modeled from 50 to 54 megahertz. Now notice that the peak of this antenna, which is better than 1.1 to 1, which is excellent, that peak here, this is in the place where you'd be working SSB or maybe CW. Okay, it rises up, it goes a little off the screen here, but it still stays below 1.5 through the rest of the band. There's another minimum, which it happens to be even stronger, at least in the modeling, out here above 53, and then it rapidly blows up toward the high end of the band. And that's what happens with this particular design. And I don't really care about this very high end of the band necessarily, and so that's what you get. Now we'll see later on this can be tuned a little bit by adjusting the actual elements. And the last thing here to look at is Z, and that is the total impedance. And we want that to be pretty close to 50 because that matches the feed line. And in fact we get that from basically from 50 up to about just over 53. We're very close to that. We do climb up to about 63 or so. So not too bad, not perfect, but that's not a huge difference. But down here where we're probably most interested in, we're very close to 50. Okay, so after the modeling, what I came up with was this design. And so what I have here, again, the reflector is the largest element, and that's the one that's on the back side, then the driven element, and then 2 directors. Now X here, that is in the direction, along the direction that you're sending the signal. So I define the reflector as being the 0 point. The driven element will be 2 feet 9 inches or 84 centimeters in front of the reflector. Director 1 will be 3 feet 6 3/8 inches or 108 centimeters in front of the reflector. And the second director will be 6 feet 8 1/8 inches or 203 centimeters ahead of the reflector element. And if you really wanted to, you could tweak this a little bit so that you actually went below 2 meters. Now, Y, that is the width. Okay, that's how big the element is going to be. So the reflector element is the biggest one, 9 feet 9 1/4 inches or 298 centimeters. That's very close to being half a wavelength. Notice that that's 3 meters, 2.98 meters. The driven element, 9 feet 5 1/2 or 288 centimeters. The first director 8 feet 8 3/4 or 266 centimeters, and the front element, the second director, 8 feet 4 inches or 254 centimeters. So what we're going to do here is the bulk of these elements are going to be a 6-foot section of 1/2 inch aluminum tubing. The 6-foot length is a typical length that you might be able to buy. It's also pretty much the biggest length that you can buy online and pay reasonable shipping costs, because that's going to be 6 feet long, and packages over 6 feet generally are going to start costing you a lot more to ship. And then we're going to slide sections of 3/8 inch aluminum tubing inside of that, and you'll find you want to make sure that the tubing that you get does this, because there are different thicknesses of the wall of the tubing, but you can easily find tubing, the 3/8 inch tubing, that will just nicely snugly fit into the 1/2 inch tubing. And the reason why that's nice is because that means you don't have to have one solid, 8 to 10 foot element. And that means the largest pieces of this antenna are going to be the 6-foot segments of the 1/2 inch tubing. So EXT, that is how much the 3/8 inch tubing will extend out from the end of the 1/2 inch tubing. So for the reflector, 1/2 of the element is 4 feet 10 5/8 inches. Well, half of the 6 feet is 3 feet. So take 4 10 5/8 minus 3 feet, you're left with 1 foot 10 5/8 inches, or 22 5/8 inches. Okay, so that's the overhang of the 3/8 inch tubing outside of the 1/2 inch tubing, or 57.5 centimeters. And again, these numbers just work their way down. And the shortest element, the front director, there's a 14 inch overhang, or 14 inch extension of the 3/8 inch pipe, and that's 35.6 centimeters. Now here's this antenna graphically, and this will kind of illustrate these things maybe a little better. So here's our beam. That's going to be the support beam for the elements of the antenna. And this is drawn to scale. I've got the grid paper here. So the reflector element is back here, and you see the driven element is shorter, the first director is shorter, the second director is even shorter. And then I have the spacing of these elements. And this is exactly the values that were in that table. Now the beam for this, I'm going to do something a little different. What's frequently used, PVC pipe is frequently used. That's not a bad choice. For that, you do need to be very careful when you're putting holes through the PVC pipe for the elements to get everything lined up as good as possible. Now, some people use aluminum for this, and a lot of professional commercial antennas will have an aluminum beam here. And one thing that can be done there is that this can be a square profile, a square cross-section beam, and that can work very well. So what I decided to do is I'm going to make this a wooden beam. And in keeping with this idea of making it as portable as possible, instead of having a single 7-foot length of wood, I'm going to use 2 4-foot pieces of wood and hinge them, and then I'll cut them so that they're so it's just 7 feet total. And with that hinge, then it can be folded, and that means that you don't have any pieces that are longer than the 6-foot sections of aluminum. And the advantage of the wooden beam over PVC is that with the wooden beam you have a nice flat surface on which to mount the elements. So you don't have to worry about getting all the holes exactly right, because you've got this nice plane to work with. And what we'll do in the next video is looking at the details of the construction. I'll show you exactly what I'm going to use to make those attachments, and to try to get everything as precise as possible. So I hope this whets your appetite for this 6-meter Yagi. Next video we'll go through the construction process, and you'll get to see this take shape, and a lot of this stuff will probably make a little more sense once you actually see it for real.